Okay, so when we left off, I was talking about Gauss Seidel, which is basically walking in the coordinate directions. And we saw that, as you might expect, this will tend to zigzag in problems. I won't go into the details. If you're interested, you can go back to Unit 11. But there is, you can use Gauss Seidel to iteratively solve a system of equations like we were talking about in the linear algebra unit. And so that can give you a computationally efficient way to get an approximate solution. Let's see, I guess the other thing I'll comment on here, I'm not going to go through this in detail, is that one of the ways that Gauss Seidel is used is in solving Lasso problems. So a Lasso problem is basically, or a Lasso problem, is basically you're trying to to find some parameters beta in a least squares type problem, but you want to impose a penalty to basically regularize the betas and not make sure the betas don't get too big. And so this is a penalty parameter, and this basically, as lambda gets bigger, it's basically going to penalize having large values of the coefficients. So there's a coordinate descent approach to solving this Lasso problem, and it basically amounts to, given the location where you're at, you get all the directional derivatives, and you figure out which one is the one that's headed most steeply downhill, and then you choose to do a one-dimensional search in that direction. So that's the basic algorithm that gets used. And this thing doesn't, in general, have a derivative, but you can calculate these directional derivatives where you need to account for the fact that, or that is the directional derivative. This thing doesn't have a derivative because of the singularity here, because of the absolute value. But you can calculate directional derivatives, and you just need to be careful about dealing with the situation where the absolute value function comes to a point at 0. So if you hear about least angle regression, that's basically a variation on this, and it actually allows you to, when you're doing the Lasso, you have to choose a value of lambda as to how much penalization to do. And this Lars algorithm actually is quite clever. It allows you to basically compute the best values of beta, the beta hats, for every single possible value of lambda. Okay. So let's move on. I want to talk about Nelder Mead. So we already said that BFGS is one of the main options in the optim function in R, which we're going to see towards the end of class today. The default is actually something called Nelder Mead. And the nice advantage of Nelder Mead is that it doesn't use any derivatives. So it's a derivative-free method. It tends, sort of as you might expect, given that it's not doing a Newton-like kind of updating, it's slower than if you use the derivative information, but it's more robust for the sorts of reasons that we've talked about the ways that Newton's method can go wrong. So it's basically sort of a recipe, and the basic thing that you do is you take, basically, if you're searching in a p-dimensional space, you take p plus 1 points that form a polytope. So basically, this is going to amount to taking a triangle in 2 dimensions, taking a tetrahedron in 4 dimensions, and so on and so forth. So you're sort of getting these bigger and bigger sets of points that define this sort of this region. And basically, the idea is you've got this set of points, and you're searching in this space, and you basically have these rules that tell you how do I sort of walk this region defined by the points towards the minimum. And that can also involve steps where you sort of expand the region or contract the region. And you're doing the walking and the expansion and the contraction all based on evaluating the function at each of the p plus 1 points and seeing how big the function is at each of those points relative to each other. So there are basically different kinds of steps involving reflection and expansion and contraction and shrinkage. And for each of these different kinds of steps, there's a tuning factor that controls how the algorithm runs. So I think rather than sort of concentrating on this in the abstract, I think the best way is just to sort of do a little bit of demonstration. So to set this up, we're going to need as a starting point, we're going to need p plus 1 points. And we're going to calculate the objective function on those p plus 1 points. And then we're going to assign labels 1 up through p plus 1 based on such that f of x1 is the value, that's x1 is the value at which f takes its lowest value, and p plus 1 is, xp plus 1 is the value at which it takes its largest value. And these points have to be the vertices of a convex hull, so they have to define a convex region. So let's actually walk through this. So I'm just going to, I think I just chose these tuning factors from the defaults in R in the optim function, which implements Nelder Mead. So I'm just also going to define a little auxiliary function that will just plot a line segment between 2 points. So we're going to use that. And now I'm just going to define my initial polytope, and then I'm going to plot what this might look like. So actually, let me make this one panel. Okay, so suppose that somehow or another, by some recipe, I've chosen these initial values. And I'm trying to search through this two-dimensional space to find the minimum of some function f. I haven't actually, in this example, I'm not actually going to define the function f. I'm just going to sort of walk through what the steps would be. But it is sort of illustrative, because when we have this function, the only thing that we can do with it is evaluate it and see how big the value of the function is at different points. So in some sense, looking at this blank screen and saying we have these 3 points is sort of an accurate reflection of sort of what our state of knowledge is when we go into running this algorithm. Okay, so the idea is I'm going to find the mean point between, so suppose this is where the function, we're trying to minimize, and suppose this is where the function is largest. So we're going to find the mean of the other points. And I'm just going to, so this is going to be xp plus 1. Sorry, I didn't take the time to do the jittering to make this come out very well. But so this is xp plus, this is x1, this is x2, this is xp plus 1. We can sort of imagine we might be in higher dimensions, but here we're just in three dimensions. So the first step is to take the mean of the other points, of the better points. This is the worst point. And then the first, then we're just going to sort of follow along with the algorithm here. So the first step is, well, I've defined it here as the second step, but for sort of the first meaningful step is to do a reflection. So what we're going to do is we're going to reflect from this point across this line, or a plane if it were in higher dimensions, to get a point over here. So, and that reflection is going to be based on this one of those tuning factors, in particular this tuning factor alpha that says how far to reflect across. Okay, so once I do that, I'm going to get this new point that I'm going to call xr, and that's going to define a new triangle, the red triangle. And the idea is I see how does f of xr compare to f of xp plus 1. Okay? So basically, so what do we know when we start out here? We've evaluated 3 points. I know that maybe sort of over here is bad because this is the worst point. And I know that maybe over here is sort of good because that's the best point. And the idea is, what I should check is, should I be going in this direction? Because does it mean that if this is the worst point, then maybe going in that direction is sort of the right way to go. So that's sort of some of the intuition here. So the reflection tries to accomplish that, and then you evaluate f at xr and f at xp plus 1. And let me go back to the notes just to remind myself of exactly what the rules are here. So, okay, so if f at xr, the new point, is between the best and the worst of the other points, then you're done. You want to move, you want to sort of shift the triangle across that reflection, across that line, and use the new triangle, which was the red triangle. However, if f of xr is better than all the other points, well, let's think about what that means. Oops. Can't push the right button here. Okay, so if this is better than this, but not better than all of these, then I just stick with the red triangle, and then I go back to stage 1 and repeat the iterations. If this is the best point, well, what does that suggest? That suggests that moving in this direction is a good idea, and maybe I want to move even further in that direction. Okay? So the next step is to do a potential expansion of my triangle. So this is the expansion step. So now there's another tuning factor gamma that says, how far might I expand in this direction? So that's what gamma determines. So I chose a particular gamma. So let's, so this might be my expansion. That would be my expansion point for that particular value of gamma. And so this would be the new triangle that I would use if this point were better than all the other points, and then if I checked and saw that this point was even better. I think that's, if I'm remembering correctly, that's the rule. Okay, so if f of xr is better than all the other points, expand from x of r to xe. And if x of xe is in fact better than f of xr, use xe in place of xp plus 1. If not, use x sub r. So we check both of these. Basically, we're checking these three, and if this is better than this, then we're going to go out to here. If this is better than this, then we're going to go out to here. So that's sort of our first move. We're trying to see if we should move away and in this direction away from this point. Okay, so if xr is not, if xr is worse than all the other points, then what that suggests is I might want to actually be sort of contracting down instead of expanding out in that direction. Actually, let me pause here, sort of to walk through some of the steps. Are there any questions about sort of the big picture of what I'm trying to do here? Okay, so then it says if f of xr, that reflected point, the sort of red triangle, is worse than all the other points but better than the f of xp plus 1, then we're going to define this new x of h that's equal to x sub r. And if it's worse than, if f of xr is worse than xp plus 1, we're going to define xh to be xp plus 1. So basically we're either choosing this one or this one, depending on whether f is better here or here. And either one of these, in this, from the way we're walking through the recipe, is the worst of the points. It's just whether this happens to be better than this one or not. So if that's the case, then the idea is neither of these two is particularly good relative to these other points. So I want to sort of contract down the triangle. That's the basic idea. I don't want to keep walking in this direction. Pretty sure I don't want to walk in that direction because I know this is the worst one. So I want to sort of contract my triangle down. Okay, so let's suppose that this point was actually better than this point. So I'm going to now define a new triangle based on the three original points. And this is the contraction step, and then now there's a beta in here that's of the third of these tuning parameters, and it says how much contraction to do. Okay, so basically the contraction step is to then choose a point in between here and here. And let me go back to the rules here. Okay, so contract h towards the hyperplane formed by the other points to get this x sub c. And if that's better than where I was, in this case the xp plus 1, but it could have been the xr, then I'm going to replace xp plus 1 with xc. So in terms of the picture, that says, okay, if this point is indeed better than this point, then I'm going to define a new triangle that's this blue triangle. Okay, so basically I want to sort of contract the triangle down in this direction because this one is better than that one. Okay, so if that's not the case, then there's a fourth type of move that I can make here, and that's basically to contract towards the best point. So I've been sort of doing a lot of monkeying around here, and basically the story is if I haven't been able to do very well in terms of these various options that I've chosen so far, then what it probably means is I probably want to sort of move everything towards where the best point is. So that's basically what the fourth possible move is. There's yet a fourth tuning factor, which is this delta, which says how much shrinkage to do towards that best point. And if we do the shrinkage, then we're going to get something like this, where I'm basically taking the original triangle and contracting it back towards the first point. Okay. So that's basically the strategy. So I've walked through sort of 4 different moves that we could have made. This was all part of the first iteration of the optimization. Based on that, I will have either chosen the red triangle, the green triangle, the blue triangle, or the purple triangle. I guess there could have been a couple other variations depending on sort of what was better than what as I was looking at these 4 points here. And then I get a new triangle, and then I just repeat the process. And the idea is this allows me to both sort of walk towards the minimum and shrink or expand as needed, depending on what my evaluation of the function at these various points tells me about as I'm sort of blindly searching through the space, except for these points of light where I can sort of get a sense of what's going on. Okay, so any questions about that? Okay, so that is the default in R. My sense is it usually works pretty well and is often more robust than using the BFGS method, which was that Newton quasi-Newton method. Okay, so that's a number of the algorithms. The last algorithm I want to touch on is something called simulated annealing, which is also one of the options in R's optim function. And simulated annealing is somewhat different because so far what we've been doing is we've been basically looking for ways that we can walk downhill to search for the minimum. And we've basically been always walking downhill. Okay? So the obvious danger with that is, as we've discussed, as people have raised on Piazza, what happens if we have multiple minima? Okay? Well, then the starting values are really going to matter. And so, maybe we've got some function that looks like this, and depending on where we start, we might end up getting trapped in one of these local minima and never find the global minimum. So one option is just sort of a brute force method of just trying a lot of different starting values and hoping that you end up with one of those starting values ending up at the minimum. And you'll at least be able to see whether or not which of the minima you found is the best of those minima. You can still never rule out the fact that maybe I've done this and I found these minima, but I didn't happen to choose a starting value that ever got me over here, and this is the global minimum. So there's still no guarantee with multiple starting values that I'm actually going to find the true global minimum. So the idea behind simulated annealing is to try and the idea was that people wanted a method that might work better for dealing with the multiple minima problem. So I just want to give you sort of a flavor of what simulated annealing is all about. So it's a stochastic algorithm in the sense that there's some random sampling going on in the process of the algorithm. And part of that is that we can actually go uphill in addition to going downhill. And the idea of being able to go uphill is, suppose we're sitting in one of these places like here, and if I can only go downhill, I'm just going to get trapped here. But if I can also go uphill, well, then maybe, as long as there's enough probability of going uphill and I can walk uphill enough, maybe I can actually walk uphill and get over this hump and get down into this valley. Let's, for the moment, get rid of this other one. So let's assume this doesn't exist for now, for the sake of this picture. So the idea is being able to walk uphill might be a good thing and might allow us to get out of the local minima and get in and to go find the global minimum. So that's all well and good. As part of being able to get over these humps, one of the ideas is that if we could sort of flatten the function out a bit, it might actually be easier to go uphill and get over the humps and fall back down into the valleys. So part of the idea of simulated annealing is that there are going to be some iterations, and in the first initial iterations, we're really going to flatten this function out such that the peaks and valleys are really not as accentuated as they initially are. So we might sort of flatten this function out so that it looks like this. I'm trying to draw this so it still has the same sorts of minima, but is sort of flatter. Okay, so I've sort of flattened this out, so this is still the global minimum, and hopefully these are all still in relative heights relative to each other. But the peaks and the valleys are less accentuated than they were here. And the idea is if we then apply an algorithm that can walk uphill, that we're going to be able to move around this space much more easily than we could here, where we would get trapped in the local minima. Okay, so then the idea of simulated annealing is that you have basically a tuning parameter that walks you. I sort of drew this in a bad way, but suppose this is step 1, and this is step 10 or something like that. Or I guess this is the final function, so this is sort of the last step. And the idea is that as you change the steps, you're going to let the sort of flattened out function get closer and closer to the original function. So you're going to go from really flattening it out to going back to getting to the original function. And the idea is if you do the walking through the space at each of these steps, the idea is as you do this is called cooling. There's an analogy to metallurgy here, which I don't remember all the details about. But the idea is as you do this cooling, as you go from the flattened function back to the original function, that you will reasonably likely end up, as you're doing this process, in the global minimum. And then as you get to the actual function, then you actually get trapped there in the global minimum, and you're unlikely to step out of that valley at that point. So that's sort of the basic heuristic of what's going on with simulated annealing. These are more of the technical details, and I'll just say a few words about this, which is the way that you do the flattening is you take the you basically, well, that's sort of the algorithm of how you make use of the flattened function. But the flattened function is basically you take f of theta, and so let's assume we're trying to maximize f of theta. So suppose, say, this is a likelihood or a log likelihood. Then to get to this version where we're trying to minimize and we've flattened it out, we do exp of minus f of theta divided by tau j. And tau j is the parameter that determines how flattened this is and how flattened each of the different steps is. So j is indexing going from step 1, step 2, step 3, and so on and so forth. Okay. And the actual algorithm when we're in any one of these steps is that you basically set up a Markov chain Monte Carlo algorithm, which is some of you have probably heard of as one of the main algorithms used for doing for fitting posterior distributions in Bayesian statistical models. And what an MCMC does is basically you're at a current place, let's call that theta t, and you have what's called a proposal distribution that says, how do I move away from theta t? And then there's an acceptance decision that says, there's a rule that says, if I propose to move from theta t, and I think I use theta tilde in here, if I propose to move from theta t to theta tilde, there's a rule that says whether or not I accept the move or I reject it. And what that rule does in heuristic terms is if you're proposing to move, in this case, downhill, you'll always accept. But if you're proposing to move uphill, you'll sometimes accept and sometimes reject the move. And the more uphill you're going, the less likely you are to accept. So that ability to move uphill combined with the flattening is this idea of being able to move between the modes of the function. And then as this thing goes back to its original form, then you're less and less likely to be able to go as far uphill as you would need to jump out of one of the modes and into another mode. And so the idea is to sort of hope, and there's some results that back this up, to hope that you'll get trapped in the local minimum. So this is fairly sensitive to exactly the schedule by which you go from the step 1, the flattened one, back to the original function, and that basically is. The schedule is basically what the sequence of tau 1, tau 2, tau 3 up through however many steps you end up using. So there's been some work on this, and people have come up with sort of recipes for how to do this, how to create these schedules. Okay, so I think that's even with, I guess the last thing to say is even with this approach, it's still helpful to have multiple starting points and to run the algorithm from multiple starting points. Okay, so any questions about that? Okay, so we've seen a variety of different algorithms. We've seen that a lot of them can be related back to something that's like Newton's method in various sort of forms or flavors or transformations. And if we look at the help on the optimum function R, we've seen that we've actually talked about several of the primary methods that get used in optim. So you have the option of choosing amongst different ones, and some of the ones that people commonly use are Nelder Mead, BFGS, and simulated annealing, all of which we've talked about to one degree or another. So what I'd like to do, probably for much of the remaining class today, is basically sort of walk through a more practical example of how would you use the optimum function R. What are some of the options in that function, and how do they relate back to some of these themes that we've been talking about as we've been talking about particular algorithms? So first, just as an overview of what some of the different functions are. So there's a function called optimize, which is pretty good for one-dimensional optimization, and it's based in part on golden section search, which we talked about right at the beginning of the unit on optimization. Remember the phi and the 1 minus phi, and trying to make sure that we're removing the same amount from our interval at each of the iterations. There's also a function called uniroot that finds the zero of functions, so we could do optimization based on taking the derivative and then finding the root, which we talked about in relation to Newton's method. I've already sort of said optim is one of the sort of the go-to methods for one of the go-to functions for optimization in R, and we're going to see that in some detail in a second. There's another multivariate one optimization method called NLM, which also uses a Newton-style method. So that is another option. And then there's this recent package called OptimX, which has come out, which basically will allow you to run a variety of these different optimization functions on the same problem. And that's often a nice strategy to use to basically sort of give you a more robust optimization by trying a few different methods. So that's another tool that's out there. Okay, so let's see what some of these options are. So 6.2 basically just walks through talking about what some of the options to the optim function are, and we're just going to sort of walk through those in an actual example. So let me just tell you a little bit about the example that I'm going to use. So this is it's basically an example from climate science, atmospheric science, and it basically has to do with thinking about extreme weather events. So the basic idea is that, and I'll do an example with precipitation, so I'll talk about precipitation. So the idea is you might think about thinking about what the density of, say, rainfall is at a given location in a given place. So if there's a weather station here on campus that's, I don't know, a few hundred yards that way. And so you might take the data from that weather station and look at precipitation. I guess that would be all rainfall here, but in other places that would include snow. Take the amount of rainfall on every day over the course of however long they've been collecting data at that weather station. And that would give you, if you plotted out that in terms of the actual observations, you'd end up with some histogram of values where there'd be a spike at 0, and then you'd have some distribution of values of rainfall. And once you get out here, you're getting out into the tail, and you're looking at these extreme precipitation events where you get a lot of rainfall on any single day. So there's a sub-area, there's sort of a sub-discipline in statistics called extreme value statistics. And what extreme value statistics does is it looks at ways to model the tails of distributions. And the idea is that knowing what's going on in the bulk of the distribution might not tell you very much about the tail of the distribution. So the idea of one of the methods in extreme value analysis is basically to choose a threshold and only consider the data above that threshold. And then the idea is to use the data there to basically describe the distribution of, say, in this case, precipitation, of extreme daily precipitation. And one of the things that people are very interested in doing based on this is basically trying to extrapolate out and say, what is the most precipitation we might expect to occur within a 20-year interval, or a 50-year interval, or a 100-year interval? And you can imagine this might be useful for things like planning for sewer systems, or planning for other things like that would be affected by floods, or planning for how would you increase the size of the banks of rivers and things like that. So there's a lot of interest, particularly with climate change, in being able to say, how likely is it that we might see a day in which we get 10 inches of rainfall in a given day? Or what's the most rainfall we might expect to see in a day over the course of the next 100 years? So people basically fit distributions to the tails of these kinds of data sets and then use those to sort of extrapolate out to sort of interesting places out in the tail of the distribution. And there's some statistical theory that says if you choose a high enough threshold, then basically you can describe the distribution in the tail, basically sort of regardless of the generating overall distribution. You can basically describe it with a 3-parameter family of distributions. So it's sort of like the normal distribution, except it's not a normal distribution. It can have fat tails, but it has 3 parameters, and it's basically widely, it can be basically widely used for these sorts of data. Okay, so the likelihood for that distribution is, it has 3 parameters in it. Part of the reason I'm using it here is it's not too complicated, but it is more complicated than a simpler problem would be. So in this particular case, the likelihood is exp of ny 1 plus omega c minus mu over sigma minus 1 over sigma times the product I from 1 to n Okay, so this is the number of years that I have data for. And the n is the number of values that exceed this threshold, which I'm going to call c. And that's the c that's in here. And then these xi's are basically all of the observations that fall above the threshold. So this mu is not a mean because in some cases this distribution is going to have a heavy enough tail that there's no expectation. But mu is basically sort of the center of the distribution, sort of a location parameter. And sigma, again, there might not be a variance, but sigma is basically a scale parameter, so sort of like a variance. And c is a shape parameter, and it determines basically how heavy the tail is, how fat the tail is. So you can go from having basically a tail that is bounded, where you can't get any values above some particular level, to having a tail that's basically like a Gaussian that decays exponentially, to having a tail that is a fat tail that decays basically polynomially like a t-distribution. Okay, so we sort of in some ways didn't really need to see the details of this function, except to see that there are 3 parameters in it, and it's a fairly complicated function in terms of the function of those 3 parameters. So let's see how we might go about optimizing that function using R's optim function. Okay, so before I get to that, any questions about this motivating example? Okay, so here are the data. I believe these are from this Berkeley weather station, although since I did this a couple years ago, I'm now forgetting the exactly where they came from. Turns out the data set is in hundredths of inches, so I'm just changing it to be in inches. And if we plot the data, they look something like this. So this is a histogram of the original data. You can see there's a spike near 0, and then it decays off. And if I choose a threshold, which is basically the 98th percentile of all the days that have any rain at all, that basically sets a threshold that's right around 3 inches in this particular case. So we can say that sort of any of the values above 3 inches a day is a fairly extreme day. That would be a very wet day. And we're going to look and analyze the data just that are wetter than that. And you can see there's actually not very much data here. There's 8 values in this bin, 4, 3, 3, 2, and 1. So we're dealing, once we start to analyze extreme data, there's not very much of it, by definition. Actually, this is just the data from precipitation during the winter, which is one of the seasons, well, the main season where there tends to be more rain here in Berkeley. So this is just setting up the threshold, defining this NPY is this. No, that's not quite right. NPY is the number of observations every year. So I'm going to write out my likelihood function, pp.like. This is going to be on the log scale because, as we've discussed, it's better to do the optimization on the log scale. And what does it look like? Well, it basically needs to take a single object as the first argument. That's going to be the parameter vector. And then these other things can be additional arguments. But then what I'm doing here, and it's often sort of a nice thing to do just from a coding practice perspective, is I'm then breaking apart the parameter vector and assigning the elements to have meaningful names. So so there's the mu, the scale, and the shape, which is c. And then I write out what the log likelihood function is. Okay, so that's the first thing I need. And now I'm going to use Optim to try and find my parameter estimates. So what do I need for Optim? Well, the arguments are, I need to give it a vector that's the initial values in the same order as the values that are going to be used in that likelihood function that we just saw. And I need to give it an R function, in this case that pp.like function that actually evaluates the likelihood. And then here I'm saying, oh, I do want the Hessian returned at the end of the Hessian at the minimum. And in this case, I'll use BFGS as my method for doing optimization. And then there's some control options that basically say sort of what should I use as the maximum number of iterations. And in this case, I think trace equals true is going to print out sort of the steps as it goes along of doing the optimization. So that's the basic idea. So here I'm going to just choose the observations that are higher than the threshold. Sorry, I'm using y here, and I used x there. But the y exceedances are just all of these observations. And then we've talked about the importance of initial values. So here I have some recipe by which I choose initial values for this particular problem. And I'm doing that. So here's init 0. So 3.5 is that mu parameter, 0.68 is that sigma parameter, 0.1 is the shape parameter. Basically, this is based on me having done this sum before and having some sense of sort of what reasonable values of the shape parameter are in terms of the tails of these kinds of distributions. But in terms of that's a little bit hard for you to assess without sort of having a little bit of experience with this. We can look at these numbers and say, just sort of as a ballpark, do these numbers make some sense as initial values? Because we've just said that the mu is basically sort of the center of the distribution, and sigma is sort of the scale on a sort of standard deviation kind of scale of the distribution. And so if I look at this, I say, okay, 3.68 or whatever it is, 3.56, that's not too bad as the center of a distribution, accounting for the fact that there's sort of a spike here and then sort of a tail out here. And if I'm talking about sort of a standard deviation or something that's roughly akin to a standard deviation, 0.7, maybe that seems a little bit small here, but maybe that's at least in the ballpark of order of magnitude of what it should be for this particular problem, based on seeing what the range of values is here. So that's the sort of, that's sort of part of the exercise we need to go through is sort of try and come up with initial values and try and convince ourselves that they're at least sort of roughly in the ballpark of what might be plausible parameter values. Okay, so I've got the initial values. I've got my likelihood function. I've got basically what's going to happen here is these guys here, if we look at help on the Optim function, we'll see there's a ... argument. And basically these things here that don't correspond to arguments that are names for the arguments of the Optim function will just get passed along to the function that's being optimized with respect to. So the thresh and the NPY are just going to get passed along to pp.like and used as part of pp.like. Okay, so now we can go ahead and do the optimization. Oh, it looks like in this case I'm starting out by using Nelder Mead because I'm not changing from the default. So we can just sort of get a sense of what it says. So it evaluates the likelihood function, the log likelihood function for the initial parameters and gives us this. So there's something, I'm not sure what that means by the scaling, but this says something about what the tolerance is that determines when we've converged sufficiently to finish off the iterations.
So why do we pass in the floor y instead of the y string in this?
Oh, yeah, that's a good question. I think that's just because of how I happen to set up the this pp.like. So it looks like I wrote this pp.like in a somewhat general fashion such that I can give it the full vector of observations and a threshold, and then I do the thresholding within the function. But you could choose to do this in different ways. Yeah. Okay, so you can sort of see that what it's giving out as this trace of the procedure is basically, you can sort of see these relate to the Nelder Mead. And there's a reflection, I don't know, there's the reduction, there's an extension, so these are more or less the terms that I was using when we talked about Nelder Mead and these various triangles. Right? So it's sort of walking its way through the space, and eventually it has it reaches its convergence criterion, and it says, okay, these are the estimates. So 1.92 is the location, 1.38 is the scale, minus 0.2 is the shape. The value of the objective function at the minimum is 61. It evaluated the function 118 times in the process of doing this. And it has converged. I'm pretty sure that in this case, convergence being 0 means that it has converged, even though in R we often say that 0 is false. So that's what we get as our maximum likelihood estimates for this particular problem for that optimization method. So we could also do this, and like I've said, it's good practice to try a couple different methods on the same problem and see if we're converging to the same minimum. So we can do this with BFGS. I'm just changing the method here to be BFGS. And again, it says it's converged. It says it evaluated the function 43 times. It evaluated the gradient 13 times in terms of doing the Newton-type steps. In this case, I didn't give it a gradient function. I could actually give it an actual R function that evaluates the gradient, that is the analytic gradient. But if I don't give it that, then it's going to use it's going to do numerical differentiation to estimate the gradient, and we'll talk about that in the next unit. And if I look at what the optimum is, and I look at the parameter values, I'll see that they're essentially the same as what I got from using Nelder Mead. So that's pretty reassuring that I'm getting the same thing. So 61.41095, 61.41095. So it looks like it's the same up to maybe 6 or so decimal places in this case. If I wanted to, I could sort of play around and see, does it really make much difference in terms of how long each of these takes? And in this case, this is a really fast optimization. It doesn't take very long to evaluate the likelihood function, and I'm only optimizing with respect to 3 parameters. So it's not all that hard a problem. And in this case, it only takes about 0.1 seconds, either for the slightly slower Nelder Mead or for the slightly faster BFGS. So another thing that I've said is it's a good idea to try different starting values and see if we end up at the same place. So here I just have a slightly different recipe for arriving at what the initial mu and the initial sigma are. I think maybe this might be in a different shape as well, I forget. And so I can just run through this and see, do I indeed get the same thing? It does look like they're essentially the same thing, the 61.4095. More or less, looks like a little bit different here. And if we looked at these parameter values, we'd see they're essentially the same as we got before. And again, I could do this with BFGS, and again, I'm getting the same thing here. Okay, so now let's see if we can sort of break this and see what happens when things go wrong. So I'm sort of going to artificially tweak things to see, just to sort of play with this and see what happens if things go wrong. So the first thing is, let's try and see what might happen if I chose some bad starting values. So how am I going to choose bad starting values? Well, in this case, I'm going to choose the location parameter to just be the threshold. So that maybe isn't all that bad, but I'm going to choose it to be that. But critically, what I'm going to do is I'm going to choose the scale to be 0.01. So that seems quite small, and orders of magnitude smaller than it should be. So it's basically saying all the data should be really sort of clustered around here, when in fact the data are much more widely spread out. So I'm trying to act as if I'm sort of going into this naively, not thinking about the problem, and just sort of choosing a value without being careful about it. So let's see what happens here. So this is using Nelder Mead with the bad starting values, and you'll notice it says exiting from Nelder Mead. Let's see what it. Okay, so in this case, it looks like Nelder Mead worked fine despite the bad starting value. So I still get this same set of parameter values. I still get the same value of the objective function at the optimum point, or what I'm hoping is the optimum point. If I want to, I can take the Hessian and invert it and get out estimates of the asymptotic covariance matrix. And if I took the square roots of these diagonal elements, I'd have the asymptotic standard errors from the problem. So, those are sort of on the right scale. I get a standard error of 0.26, 0.44, and 0.05, where the parameter values are. So I had 1.92 with a standard error of 0.26, and then I had, I think, I don't remember what exactly it was. I had 1.38 with a standard error of square root of 0.44, and then I had, I think, minus 0.2 with a standard error of square root of 0.05. So at least just sort of ballparking those numbers, they don't seem crazy in terms of the size of the standard error relative to the magnitude of the estimates. Okay, so now let's try and do BFGS with those bad starting values and see what happens. So, okay, well, it says it converged. That's reassuring. But wait a minute. It says the final value is 80.98. Right? Remember, we've been getting something like 61 or 62 as our optimum for the other times that we've run the optimization. And if I look at out, that out was for Nelder Mead. Out 2 is for the Hessian. I mean, sorry, out2 is for BFGS. Ah, okay. So things have now changed. I'm getting very, very different parameter estimates. The mean is said to be -4. That seems a little bit crazy relative to this. And the location is said to be -4. And the scale parameter is 26. So it's converging to some other local minimum that says the best way to describe these data is to put the location parameter way out here and have the spread, the scale, be really, really large. And then if you guys don't know this because you haven't looked at these models before, this is a very extreme value for the tail, for the shape parameter. And we can see this is not the global minimum because it's worse than the previous one that we had been finding. And so if we had just used BFGS and we had just used these particular bad initial values, we wouldn't know. We'd look at this and be like, okay, it converged, it gave us a minimum, I'm going to report that as my maximum likelihood estimate, I'm going to write my paper, and I'm done, right? So you can go pretty badly wrong. And in this case, it's very badly wrong, because if we actually tried to get the asymptotic covariance, we'd pretty quickly see that something weird is going on, which is that the Hessian has very, very large values here on these, there are very large values in the Hessian. If I invert the Hessian and get the asymptotic covariances, a couple things pop out at us here. So one is these are really, really small, 4 times 10 to the minus 12. So if you think about that as a standard error, that's something like 1 times 10 to the minus 6. That's a really small standard error relative to the magnitude of those parameter estimates. So either you say, with 20 data points, I've nailed my parameter estimates incredibly precisely, or you say, wait a minute, this is crazy, that can't possibly be right. There's something weird going on with this optimization and with the minimum that I've converged to, and maybe that's not the global minimum. And also I get a negative asymptotic variance. This presumably has something to do with numerical issues of the sort that we've talked about, that presumably these are all essentially 0. It's just in this case because of the numerical difficulties in working with the size of these numbers and the inaccuracies involved in doing so, I've got an estimate of a variance that's negative, which is also obviously implausible. Okay, so things can go pretty badly wrong if you choose bad initial starting values, and if you're not careful about trying different initial values and trying different optimization methods. Let me see what else I want to say here. Why don't we quit there? I have a few more of these cases of sort of playing with this and trying to break the system, and we'll look at those on Monday. And then once we finish with that, we're going to switch over and start talking about the EM algorithm, which is going to be useful for the problem set, and various other ways of doing constrained optimization and dealing with convex optimization.